Okay, so today we're going to be taking you or giving you an overview of battery energy storage system. And with me, I have my dear colleagues, Harry Thompson and Sanjo Ale, that are going to be covering or supporting during this. Sorry, don't know what's happening with technology nowadays. Can you hear me?
We can hear you, yes.
Yeah. Okay. So I'm going to be talking about introduction to BESS technology. Then Harry will be giving you a bit of an overview of the battery chemistries, and also some discussion about hybrid design options, usable energy, degradation, and thermal considerations. Then I'm going to be back talking about network and power distribution. And Sanju is going to be giving you an overview of alternative storage technologies, investment and project development, and finally the best different best markets. We have a dedicated Q&A session, and obviously depending on how the time goes, you guys feel free to keep your questions to the end. But let's just try and. But I don't know how, but if the technology works. But if you want to keep it informal, and Jorgos, obviously it's only you, the one on the call, like active in the call. So or either raise your hands or feel free to interrupt if you guys have any question. So don't feel that you have only to wait to the end. So to get us started, introduction to battery technologies, we first need to understand why the need of energy storage, what's all this fuss about batteries and whatnot. So first, we start from what's the problem. So what is happening is that you have your conventional thermal plant retirement and larger penetration of renewable energy system, both at distribution and transmission level, which is going to cause a lot of imbalance in the grid. As we can see in the power market in Greece, based on capacity shared by technology, we're going to have the retirement of the lignite phase out around 26 to 28. And obviously, you guys are going to be losing a lot of the dispatchable capacity. It's worth to emphasize that the lignite in terms of pollution is worse than your standard coal, which I'm sure you guys are more than aware than also. This is very important that you guys have quite strong ambitions to retire and accelerate the retirement of these conventional thermal plants by increasing the penetration of renewables. Then we have the solar and wind being dominant by 2030, around 2030, with approx 81% of renewable energy system capacity in terms of your target. And obviously, this can be incentivized to pretty much max out your distribution level and transmission by having more PV system and wind connecting at this level, which obviously is going to have a bit of a flexibility gap and in terms of while these thermal plants are being retired. What happens of retiring these conventional thermal plants is obviously you start creating what we call the energy imbalance, which is going to be one phase of your problem. And sorry, your noise is coming back again, Jorgos. Your background noise, Jorgos.
Is again?
Yeah. So you have your energy imbalance, and why is this happening? And this is quite common in countries or regions that you have large penetration of renewable energy sources. Why? Because there is no control of the environmental condition, which I'm sure the students know by now. You're going to have your sun pretty much having pumping the generation into the grid during noontime, solar time, and then your demand normally happens during evening time. Unfortunately, because there are no ways that you can capture this excess of energy or to shift it to match the demand, you're going to have a surplus. And we can see here in a snapshot in Greece in January and September in 2024, where you see that surplus represented by the green line of electricity that has been generated by solar that obviously doesn't covers the demand but exceeded far. more than what is needed. This creates a fundamental problem for your grid operator because obviously they need to put this energy somewhere. And how they do that, they're just going to curtail. So curtail means that they're going to restrict your plans to generate, or they literally are going to turn them off. If we get closer to time to the 6th of April, you can see that this shape, and actually you can see that even in September and 2024, you start seeing this shape, which you may be familiar as the duck curve effect. This is being heavily studied since the days of when it was first introduced in California. And this is naturally happens for those countries that have large penetration of renewable energy projects, particularly in solar, that you have an increase of electricity generation, we also will have an impact on the prices of the electricity, bringing to some cases to negative prices, which I don't know whether if you guys follow the electricity market, but recently, last week and this week, we have seen a lot of electricity negative prices across Europe and in the UK as well. But what happens is that the deeper the duck belly gets and the steep the head gets, they start creating more problem to the grid operator because by having to curtail this energy, and they also have to increase the cost of the electricity, and they have more on control of having a perfect balanced grid, and they rely more on having to call your conventional thermal plants. And as a result, obviously everything gets more expensive. You guys and us, the end consumers, are the ones that have to pay the bill. So you can see here in 2024, around almost 4%, 3.4% of renewable energy generation curtailed to almost 900 gigawatt hours that literally is just wasted and dumped. And in 2025, that got almost double to around almost 2,000 gigawatt hour worth of gigawatt hour of electricity again wasted in a single year. That translated in loss of revenues for PV plants around 10% of the total output curtailed, 25% of revenue losses, equally for wind, 4% curtailed, 8%, approximately 8% of revenue losses. Obviously, this is not only in Greece, and I don't want to sound like Greece is being inefficient here. This is very common in countries where you have a large penetration of renewable energy for the likes of Spain, Portugal, and Germany too. And what happens again, increase the gas generation in the same period, it shows that there is an efficiency because what the aim is to actually retire, not having to depend in these sources now that have become quite expensive. And the other problem that we have is as you know, the grid is all about to keep it at 50 hertz, and that's in Europe, and the same as in the UK. It's slightly different in America. But what we need is that frequency has to be almost perfect all the time, and that takes a lot. And a lot of that depends and is heavily linked to your conventional thermal plants and how you have rotational synchronous machines that can allow for these frequencies to be always balanced. The more you retire these and the higher you have the penetration of variable renewable energy sources, your keeping the balance of your frequency becomes more difficult. What happens is you have a fall, you have a dip, and then your frequencies start deviating from the dead band. So in those countries that you have an active energy market, you or the grid operator procure these services through the market to be able to stabilize the grid. So thankfully, Greece is now part of the Picasso platform or the Picasso market. I think it's 2025, and is what we see in the European Union, that you have your three main services. Your primary reserve is when you are getting something is shifting and that is getting into the dead band, and you or the grid operator procure the services through the primary reserve. Then you are within the deadline, you procure fast services on the secondary reserve, and finally, to keep after full, if for anything happening, you go into the tertiary reserve services. And obviously, this problem is, and having the retirement of your thermal, there is a great solution is by increasing the penetration of energy storage. Why? And for the like of battery energy in particularly, mainly because of the response time that batteries can have and how cost effective they have become. So we have a problem that is now covered by a solution. Then if we have an opportunity of a viable product, which is the case for battery, especially for the lithium ion or iron phosphate at the moment, because of the cost efficiency that we have, then you add a bit of a market. That's an ideal case for having your business case. And this is what we are trying to maximize with battery projects by having the access of batteries to be able to take advantages as much as possible of any possible opportunities within the energy market. What happens is that batteries are too good to be true, that the grid operators have to restrict actually batteries because otherwise they will have a monopoly and they will not be able to compete to other technologies because the advantages that they have. And Sanjay, my colleague Sanjay, is going to be talking to you a bit more about the different opportunities in market and revenue models that we use in the UK and the case of Greece. So getting a bit into more the technical elements, into the chemistry, and Harry will touch a bit further into this topic. We have the main one that we currently use in battery energy storage system, which is the lithium iron phosphate. So first, we need to understand lithium. Lithium is an alkali metal, part of the group 1 or the lithium family in the periodic table, highly nuclear stable, and this is why it makes it so attractive in the electrochemical properties. Why? Because it has two electrons in its inner layer and one extra electron in the outer layer, which is the one that it always wants to share. It's always so unstable that whenever he has the chance to share that electron. And that is why it becomes so efficient in electrochemical properties again. It's an abundant but finite resource, mainly found in Chile, Argentina, and Bolivia. This is the area that we call the lithium triangle. And this area is very particular because the lithium is found actually in brine pools. So it's very easy to extract the lithium by just using the sun to evaporate the brine. But you also can get it in rocks, embedded in rocks. And obviously you need, it's more the subtraction or manufacturing is more electricity dense and polluted because it takes more to have the same volume of extraction. And you also can find them in Uruguay, the Republic of Congo, and in the deep sea. The deep sea is hopefully an area that will stay alone. And I cannot imagine all of the impacts that it's going to have in terms of pollution, but not only that, it's not the tension in terms of geopolitics that might actually make it very, very difficult. But some research indicates that actually the amount of lithium that you can get in the deep sea, it could be even double or triple to the amount of lithium that we have above the deep sea. It needs to take us, and I don't want to take you too much of your time, but we have been working for batteries from ages ago, from the late 1500s, early 1900s. Actually, your first car ever invented, and this is a fun fact, it was an electric car. It was no Elon Musk or any of this nonsense. But it took us to around 1983 for, thanks to the work of Stanley Whittingham, Sir John Titinoff, and Akira Yoshino from Sony, to actually look into the properties of lithium and to see the benefits that they can, how to make mass production for portable equipment that could use batteries for the like of cameras and phones and what we see as today. Basically, what we have is a battery cell in which you have your cathode, which is your positive side. In here, we have the metal oxide, your iron phosphate, And then you're going to have your anode, which is the negative part, your graphite. This is pretty much, if you want to see it as a car part, this is where you're going to store all of your electrons. Then you need to divide the two poles, and you're going to have that through an electrolyte. Is an aqueous solution made of chemical compounds, sodium chloride, nitric acid, to name a few. And this is what we call a liquid separator. Nowadays, technology is evolving a bit where you have actually solid state batteries, but that's not something that is heavily commercialized at the moment, but it's going to be one of those that are going to become quite soon. And in a very simplistic term, if you were to have an energy source and you connect it, you repel the electron from the lithium ion, and then your positively charged electrons move to the other state to have a perfect equilibrium state. And then and at that moment, your battery is fully charged. If you were to connect the load and to measure the voltage, your normal circuit voltage or DC voltage of lithium is anything between 3.6 to 4 volts. So moving into the composition of actually your battery containers, as we call it, and I'm going to give you just a brief overview, because to get into every single item, we might need to have another couple of webinars. But the most critical ones is your battery cell, as I mentioned, and they come in a shape of cylindric, pouch, or prismatic. Nowadays, it's more conventional to see the prismatic because it's easier to transport, to also cool them down because you have uniform areas, and also to move them inside the battery module, which your battery module is several battery cells connected in series and in parallel to increase the current and also to increase the voltage. You encapsulate them in a metal box, and that's going to be your battery module. The example that I'm showing you here is a typical battery module from CATL or CATL, one of the main brands or manufacturers of battery technologies. I put here a nominal capacity, 50 kilowatt hour. This is a bit outdated. It's just for being simplistic and just give you an example. But nowadays, the goal is to have the largest energy density among the suppliers. What that means is having the much energy capacity within the same area. Now you can see even developments that go 500 kilowatt hour, 1000 kilowatt hour, which Harry is going to probably mention a bit more. Then you put these battery modules together, just literally stack them up, and then put them in series in parallel again to increase voltage and current. And these are what we call the battery racks. And then your battery racks together inside a container is a battery container. So moving into what is the brain of your BESS system. You have the heart, which is your battery, your DC element, but the brain is going to be your power conversion system, or what we call simplistic PCS. A PCS is basically having equipment that convert electricity from DC into AC and vice versa, AC to DC for the case of battery, what we call bidirectional. For the solar case, it's one direction because normally it's just DC to AC. What it does is that you have, well, in this case, two level converters, which is the most typical one that we use in the industry at the moment, but you can have single or three level converters, which tend to be more expensive. And in simple terms, is your inverter or PCS is just transistors and or switches that are just open and closing very fast. So you can have, or either to change the flatness of the DC current into the AC, the sinusoidal wave, or vice versa to smooth out the curve of the sinusoidal waves into flat. So you have your transistors open and close. You then change the direction, and then you have the top and bottom bed of your sinusoidal AC curve. In this case, for a single phase. If you were to be three phase, well, you're going to have the same, but for each phase, you're going to have your transistors open and closing. The key material at the moment, the most common used for the transistors, and this is what drives the cost of a PCS, is your isolated gate bipolar transistors, or IGBTs, made of silicon. They have been great used in the industry for ages. The only issue that you have for the use of PCSs is that their heat exchange, they have to remain or to generate a lot of heat because of the time that they have to open and switch, that the heat exchanges or the heat property to exchange or to cool down are not that great. And you tend to see that these best PCS, especially the ones that we call center inverters, tend to be quite chunky because they need to have a space allowance to improve the heat exchange. Nowadays, the industry is moving to the silicon carbide metal oxide semiconductor field effect transistor, or easily called the MOSFETs. And the costs are coming down, which is making it more attractive. But one of the key factors is that it improves efficiency, but also improves the heat exchange within the PCS, and also a bit in terms of the response times. Although in generally PCSs are very fast. In terms of the type of PCS, we have the grid following. As the name says it, the PCS is following the voltage of the source. It needs a voltage source to be able to operate. So how it does is based on the voltage, the current, it will follow the angle to adapt to whatever it needs to synchronize. And then you have the grid forming, which basically can create its own voltage source. In other words, it doesn't need any reference. It can control and synchronize to whatever is needed through the droop control, whether through a virtual machine and inertia, and through the virtual oscillators, which are the key main points of your grid forming capabilities in a PCS. Even though that this technology has been studied and has been in R&D for a while, in terms of commercialization, it's relatively new and is being widely adopted by different Greek codes, to name Greece as well, that is promoting quite heavily because of the importance that it's going to have, especially nowadays with the retirement of the conventional thermal plants. To give you a very high level overview of the tools and how beneficial it would be for Greece, well, as I mentioned, the control mode, the following inverter is based in a current source, and your grid performance is voltage source. These are what they can create within the equipment. And obviously, these enables Greece with the grid forming capabilities to have stability with the grid. In terms of grid reference, yeah, for the follow inverter, you must have the grid available. Otherwise, in a case of a blackout following, they would just trip because they cannot sense the voltage source and they don't have any reference point and they cannot work. For the grid forming, you don't need to have a reference point because it has its own capability, and that is why it becomes critical for any grid as the thermal plants retire. Then you have your synthetic inertia. And for those electrical minded, the term synthetic, it becomes a bit of a debatable point, and I don't want to get into that. I'm more mechanical orientated. For us mechanical orientated, it does make sense because it makes such a difference as your conventional inertial coming from rotational machines. But just for the purpose of the presentation, we're just going to be using synthetic inertia to make that distinction. Follow inverters are not capable to provide this, and grid forming, yes, through virtual inertia, the droop loop control. And this is very important for the rapid change of frequency issues that you will see, or you see often in the grid, and not only in Greece, but in any other countries, especially again, those with a larger penetration of renewable energy sources. Then the fault current contribution is very limited on the follow inverter, and it's very high in the grid forming, fast injection. And this is very important for the transmission and distribution because it protects the grid against any fault level that might come from equipment or generators connected to the grid. And this, for me, is probably one of the most important functions that grid forming has, which is the black start and east landing. And you cannot do any of these services with follow inverter. You definitely can do with forming. And obviously, this enables restoration, microgrid, backup, and more importantly, increases the energy security of the country. And the oscillation damping is very weak in follow inverter, excellent in the forming, and reducing low frequency oscillation that may have by or either a large plant tripping out or having issues with fluctuations of renewable energy generators. And response time, both are very fast because, as I mentioned early on, PCSs, general converters, that's one of the beauty, and this is ideal and well placed for those ancillary services and stability market. Very quickly, how is this put into practice? Then, and contractually, you will have typically the best work and the best supply contracts. In here, your battery supplier will provide the battery containers, PCS, and medium voltage transformers in some of the cases. Then you're going to have your balance of plant contractor who is going to be doing the BOP work. In other words, the civil and electrical works on site, the guys who are going to be building the project. You may need another transformer to get to higher voltages, especially those connected at DSO level. And you're going to have your grid works, which are those related to the connection that in most of the cases are done by your DSO or TSO. So now I'm going to be leaving you with Harry, who's going to be talking about the battery chemistries.
Hi everyone. My name's Harry Thompson. I'm a BESS project consultant at Blandbos. I'm going to pick up from Andres and speak a little bit more about the battery chemistries. We'll start by saying the evolution of battery chemistries in the industry is driven by both the technical and the financial factors, and it's not necessarily the best performing battery in a lab that is seen in the field, as well as there's links between the electrical vehicle and utility scale industries, but a chemistry that's suitable for one might not be so feasible for the other. So I think just the previous slide, Andres, thank you. Sorry. So why does chemistry matter? The chemistry selected directly impacts the financial and technical aspects of the overall BESS project, determining project viability and bankability. Is a project strong enough to be funded by a financier or lender? So starting off with the cost per kilowatt hour, which is a standard metric typically measured in dollars, acts as the main benchmark to compare project financial models. It allows fair comparison between different chemistries, suppliers, and form factors, whether you're looking at cells, racks, or enclosures. The battery chemistry impacts this because whether the material is iron, lithium, nickel, it determines what the cost of that the material determines the cost. It also determines the manufacturing complexity, whether that's mining or refining, and it also dictates the energy density. How much energy is the battery storing per unit of material? Next, we have the round trip efficiency. How much energy are you losing between a full charge and discharge cycle? This matters because small round trip efficiency differences compound significantly over thousands of cycles, especially for large projects. Lower RTE reduces the delivered energy and reduces the overall revenue that can be earned by the BESS. This leads on to the cycle life, which again is fundamentally linked to the chemistry of the battery selected. Different chemistries have different tolerances for factors that impact degradation, which I'll be talking about later, but these include acceptable depths of discharge, rest time needed between cycles, and temperatures that can be sustained. This impacts the intended design life of the project and how the BESS shall be operated. Finally, and just as important as the economic and technical parameters I've just discussed, is the safety and reliability of the battery chemistry. Some chemistries are more thermally stable, more tolerant of abuse, and are less prone to self-sustaining reactions such as thermal runaway. A safer chemistry is seen as more favourable by local permitting authorities, insurance companies, fire rescue services, and the local community. These are all external stakeholders that play into obtaining the planning permit and navigating these interfaces. Safer chemistries can reduce the fire mitigation costs needed, can reduce the footprint of the BESS, and can lead to improved system availability. So now I'm going to move on to the next slide, which is looking at the sort of early era of the utility scale BESS, slightly before my time, but this was predominantly led by a lithium nickel manganese cobalt oxide, or NMC. This worked because it was a great option as it offered high energy density and had an established supply chain and manufacturing process at the time from its use in consumer electronics and early electrical vehicles. It was a quick solution that had been tested at scale and was seen as financeable. These days, there are still legacy projects using NMC batteries, but we aren't seeing any more being built and haven't for the last few years since the takeoff of LFP. One of the reasons for this is thermal stability concerns. NMC can begin self-heating at approximately 100 degrees Celsius, and once it reaches thermal runaway at around 170 degrees Celsius, it also continues to release oxygen, feeding the thermal vent and accelerating it more. This all leads to NMC having a more energetic thermal propagation than other technologies, which is a huge safety concern. The chemistry also faced high supply chain volatility, primarily due to the reliance on cobalt and manganese. 70% of global cobalt mining is from the Democratic Republic of Congo, and so disruptions, whether that's political, regulatory, or environmental, had an impact on global prices. This also raised ethical concerns with how batteries are being mined and whether there was issues associated with human rights as well as child labor. So this then sort of paved the way for LFP, or lithium iron phosphate. This works because it balances the energy density, cost, and safety. In comparison to NMC, it does have a lower energy density, but this comes with improved thermal stability and lower costs, especially as manufacturing has ramped up. Over the years, the cells have changed a lot, and we were used to seeing 280 amp hour to 300 amp hour cells, and we're now seeing this as high as 1300 amp hours, as you can see on the side. And this is a technology that has balanced those three aspects and why it has succeeded so much. Now moving on to the future of the industry, although it's unknown, we are seeing sodium ion appear as a huge contender with a projected market share as high as 30 to 40% in the future. And why is this? Well, sodium ion comes at a much lower cost and it has cost stability, with sodium being readily available compared to other materials. It can also deliver the battery technology can also deliver for up to 2 to 8 hours, and we're seeing a growing demand for longer duration energy storage, which is positive. It has a safer chemistry with respect to temperatures, and it can also deliver in a broader operating temperature, approximately minus 40 to 60 degrees Celsius, especially useful for climates that are warmer than the UK, and particularly Greece. Other contenders that we're seeing include iron air, flow batteries, or zinc-based chemistries, but these are all still developing, and in one of those constraints are falling a little bit short at the moment. So overall, each chemistry optimizes for different constraints, whether that's duration, environmental conditions, cycling profile, energy density, supply chain, and cost. The chemistries that succeed is usually one that balances them all and is not just good in one area. So now we'll look a little bit at the hybrid design options. More and more hybrid, so that's talking about co-located solar PV and BESS sites, are being developed and built globally. How we physically connect and electrically connect them to the grid is influenced by technical and commercial decisions. This is looking at the capital cost, redundancy, the use case and grid services capability, and the regulatory compliance that's available in the area. Noting that each region and network has different compliance to adhere to, which impacts the design choice. So we have our battery, solar, and a grid connection. How are we going to electrically connect them? The primary choice for this is the use case of the battery. Is the system designed to maximize the solar generation and provide energy arbitrage to the grid? Or is it to deliver grid services, stabilize the grid through efforts such as frequency response and reactive power, and maximize the possible revenue streams? The two main ways for setting up a hybrid system is the first one is a DC coupled system. This is where the solar array and DC batteries share a bidirectional inverter, also called a power conversion system, or PCS, as Anders discussed before. This is then stepped up through a transformer to connect to the grid. As you can see in the image, the green wiring shows the DC cabling. So the solar array can directly charge the batteries without needing to be converted. The provision of the DC-DC converter is in the event that the solar output does not match the BESS input voltage range and that it can stabilize it. In this system, there's only one AC-DC inverter, which handles power from both sources, and it is important that there are DC meters to track both power flow from the solar and battery independently. This monitoring is typically required by the grid operator for regulatory reasons, as well as suppliers for warranty purposes to see what the battery is actually doing. The transformer then steps up the AC voltage for grid injection, and depending on the region, this can be as high as 400 kV in the UK. This is supported with another meter, which measures the total AC power delivered and received by the grid. So now looking at the advantages of this system, it's a simple solution. There's only one conversion pathway, and this can be managed with straightforward controls. It's efficient. Again, there's only one conversion pathway, so losses associated with converting between DC and AC are reduced. And the footprint. The project can be condensed because it's sharing transformers and PCS with the solar array, so in theory, the area of the project can be reduced. Now looking at the disadvantages, the DC coupled solution does offer low modularity. The battery, PV, and the inverter are tightly integrated, and it reduces the ability to independently optimize power, energy, C-rate, and duration of the BESS. This is because the packages usually come integrated, and it limits the procurement options available. Additionally, there's typically a single point of failure. In an event where the PCS fails, both the PV and BESS cannot deliver to the grid due to the setup, increasing downtime and lost revenue. And finally, it limits the grid services that the BESS can deliver. Typically, it doesn't allow for stacking of multiple grid services, and this is because it is constrained by the single DC-AC converter, which often doesn't meet regulatory requirements. Now looking at the AC coupled system, the primary difference here is that the solar array and the DC battery have their own independent inverters before connecting to the transformer. This means that when charging the batteries from the PV or the solar array, the energy has to be converted from DC to AC and then back again from AC to DC to charge. So the primary advantage with this is that it allows operators to stack grid services, maximize revenue streams, and potential profit. This can be paid for services that stabilize the grid and can be paid on availability, so just being available, or for utilization, actually using the battery. As the PCS are different for the BESS and solar, you also have more options for procuring the battery PCS. This allows for different and or more custom setups where you can tailor the equipment to your project's needs, especially for augmentation when you're adding capacity down the line. Enhanced redundancy as well. If one of the PCS goes down, it doesn't take out large areas of the site and other inverters will still be up and running, reducing the impact of downtime and financial revenue loss. The disadvantages are the lower round trip efficiency. There's more conversions between the array and battery, leading to more losses. The site is also more complex. There's more equipment and inverters to synchronize and manage, and this leads to more sophisticated controls being needed to control the overall site. And there's also a higher capex. There's more equipment to purchase, and you have the more complex control system, which all adds up, and all needs to be considered when designing the site. So the key takeaway from this is that it's project specific, and it depends on how the battery is planned to be operated. Are you building a small 2 megawatt, 4 megawatt hour BESS on a remote island that's being used to maximize solar production during the day? Or is it a large 500 megawatt, 1 gigawatt hour BESS that's supporting grid functions and maximizing revenues? The use case depends on the coupling system, and that impacts the design decision. Moving on to the usable energy, degradation, and thermal consideration slide. So in BESS projects, we often look at the nameplate or nominal capacity and the usable capacity. Nameplate capacity is the capacity that is available for use as the product is tested and verified in the factory acceptance tests and reduces with both time and use. This is often in controlled environments. Usable capacity is what you can actually extract from the battery in field operation and is used to deliver to the grid in real life. This is what is reported to the operator of the project to determine how to use the BESS. Understanding the mechanics of degradation is how warranties are priced, operation and maintenance is budgeted, and how CapEx can be justified to justified to investors, ultimately leading to the funding of a project. So this is what a BESS project's usable capacity could look like during its lifetime. At the factory acceptance test, once the equipment has been integrated, but before it has been delivered to the site, the BESS capacity is tested and recorded. This is important for assurance reasons, and it is where the BESS will be as close to nameplate capacity as possible, with it being the 100% state of health. We then have the BESS at its commercial operations date. This is the point at which the project is ready to deliver grid services and achieve commercial operation. Since the factory acceptance test, this equipment will have been shipped, offloaded, possibly stored, installed, commissioned, energized, and will have had to pass regulatory tests to verify compliance with the grid code. In this time, the calendric degradation, which I'll come on to discuss, will have occurred, and depending on the efficiency of the program, this can be as much as 2 to 5%. Now we see the project when it's operating. In year 5, the BESS has been operating for 5 years at an average of 1.5 cycles per day. We now have degradation that's been caused through the use or the cycling of the BESS. And this continues to year 15, where the project is approaching the end of its life. Most BESS suppliers put a limit on their equipment, and that is after 60 to 65% state of health, the equipment should be disposed and recycled within the regulations of the country. So now we'll start looking at calendar degradation. This is degradation that occurs over time, regardless if the BESS is in use or not. This occurs at the beginning of the project typically, or if the equipment is stored. But there are ways to reduce and manage this. The 3 main factors are that impact the rate is the duration of time, the state of charge during this time, and the temperature. The longer the equipment is stored or sat idle, the more degradation stacks up. The equipment is typically shipped from the factory at around 30 to 50% state of charge. This is the ideal range to minimize calendric degradation. If the state of charge is too high, or even 100%, then the cells have a larger electrochemical potential, are under larger stress, and this can increase calendar aging. On the other hand, we have temperature. In our experience, the recommended storage temperature for LFP has been about -30 to 25 degrees Celsius to minimize the rate of degradation. This can increase dramatically with temperature. So if the temperature is stored at, say, 55 degrees Celsius, this can see up to an additional degradation of 0.6% per month on top of the existing degradation. So it's quite a lot in the grand scheme of things, especially over a long time. And it's important that these factors are all captured in the product warranty guarantee, and that where possible, the risk of delays can be identified and mitigated. We'll now look through the 5 primary factors for cycling degradation or degradation through use. So first of all, we have the number of cycles. So more cycles means more cumulative damage with each charge and discharge cycle. In the UK, for projects, we see this ranging from an average of 1 to 2 cycles per day. C rate. The higher the C rate leads to accelerated degradation. This is because the BESS is working harder and under more stress to discharge faster. This can be thought of in 2 ways. If you have a 4-hour system rated at 25 megawatts equals 100 megawatt hours of discharge capacity versus a 1-hour 100 megawatt system, which also discharges 100 megawatt hours, but in a much shorter time frame. The 1-hour system will face the large degradation. Depth of discharge. Operating across the full range of the battery from 0 to 100% of state of charge often puts more stress on the battery using the entire window. A more conservative approach and a way to reduce the degradation rate is to avoid the extreme ranges and discharge between 20 to 80% of the battery where appropriate and in line with the operating strategy. Temperature and the resting state of charge. As before with calendar aging, these factors also increase the rate for the cycling degradation, not only the calendar. And just for the benefit of time, I'll refer to my previous reasoning. We recommend our developers to use flexible warranties that take into account the actual use of the BESS, and we can see this here. So each year, the battery is being compared to the baseline depending on the actual use of the batteries. As raised in previous slides, temperature comes into play when determining the degradation of an asset. So looking at 2 climates, we've got the UK and Greece. The UK sits about 8 to 15 degrees Celsius average, depending on where you are, with peaks of up to 35. So this reduces cooling costs and thermal costs needed. when compared to the Greek climate, which from what I can tell is about 15 to 20 throughout the year as an average, with peaks of up to 45 at times. This means higher capex up front for stronger cooling systems. It impacts the efficiency as there's higher auxiliary consumption due to more cooling power needed, and increases degradation due to the higher temperatures. So that's a lot to think about when designing the site. Developers have different ways to protect themselves, but we recommend that the contracts have been through the correct due diligence process and are based on the real use and environmental conditions of the projects, allowing for flexible cycling. Aside from the FATs, we encourage annual energy capacity tests to determine if the project is degrading as expected. This compares the actual degradation against the modelled, which is important for the financial models of the project and determining debt repayment terms. This can then be used as a baseline through all the annual testing. I'll now pass on to, I think, back to Andres.
Thank you very much, Harry. Yeah, so conscious of time as well. So I'm just going to go here quickly through the network and power distribution. And let me see here. Okay, so first of all, I briefly mentioned early on in the presentation that we're going to have the frequency response services, or those what we call the ancillary services. So to understand where we first need to have an idea what are the triggering conditions and performance parameters. So to give you a bit of kind of an info, I choose to give a bit of comparison between the UK and what we see in Greece and in Europe in terms of the different possible services. And we have, first of all, the frequency containment. The triggering condition is the frequency deviating from your baseline of 50 hertz. In the UK, through NISO, we have the dynamic containment service dedicated for this, and your full response have to be within 1 second, and any deviation from any plus or minus hertz, 0.5 hertz for full activation. In Greece, you're going to have through the primary, and this your deadband value and anything above or below 10 millihertz, and full response within 30 seconds. Then you're going to have your frequency restoration, that this trigger condition comes automatically from the TSO or the national grid. In the UK is called the service that we have. We have actually two within this frequency restoration, the dynamic moderation and dynamic regulations, which is slightly different to the one that we see in Europe and in Greece. In terms of the response time, these are slightly ultra fast and sometimes are pre-fault, majority of the time. And anything, your response time has to be within 0.5 to 2 seconds, while this is your secondary services and it's automatic via Picasso, and full activation have to be within 5 minutes in Greece. Then you're going to have your sustained balancing, and these are services that are outside or procure the ancillary services, and normally happens through manual activation on instruction from the TSO. In the UK, we have a separate set of services through the balancing mechanism market. And in Greece and Europe, you go through the tertiary or manual activation services via MARI platform. These frequency restoration, as I mentioned earlier, these are considered ultra fast in the UK. And again, this is one of the beauty that batteries are fully capable to support these services. What we have experienced in different markets is that as soon a market emerged that allows batteries, these are the first type of services and market that batteries are going to participate, and they become very lucrative services, but they very quickly deplete this market because of the saturation by having an increased demand of battery participating, then the TSOs not needing to go these batteries. And then what happens is that these then shift into more energy services. So it's a spike in terms of batteries participating in these services, and then kind of slows down until pretty much the frequency is kind of controlled by the amount of system connected to the grid. We have the other side, and these are more on the stability and advanced grid support. It doesn't only need the grid forming capabilities, but as well grid following. This again is more on the balancing area. We have the synthetic inertia, and the trigger condition is having high variation on the rapid change of frequency, anything above 0.5 hertz per second. In the UK, your system has to be grid forming control mode, and it needs to be capable to respond anything below 100 milliseconds, which is very fast. And again, this is another of the beauty that batteries can perform very well. Um, and in Greece, where you have it through the Greek code requirements, in both in the UK, Europe, and Greece, the Greek codes are being amended, and these technologies are being slowly adapted. Because as you may know, Greek codes in all of the countries were fully against in landing mode because they needed to have for protection purposes, but now they have to change all of the relevant codes to allow the Greek forming. There is no an easy process because it takes a lot of bureaucracy and technicalities to be able to change this. We have the short circuit and fault current, and this trigger condition is going to happen through any voltage dip. In the UK, again, these are being at the moment tried, and the only way that you can benefit from these services is by being awarded contracts or through tendering via the fast fault current injection. And similarly is happening in Greece and in Europe, and this is a request for generators under the Greek code that is being evaluated. The most important, as I've been saying, the black star and its landing is when you have a complete loss. That's going to be your trigger condition, that there is a total or partial blackout in that particular network. And in the UK, again, this is being part of the restoration services that it needs to be procured through tenders. It's not an open market yet. And in Greece and Europe also is currently under the guidelines. But what is going to happen that it has to be from controlling voltage and a frequency reference that obviously grid forming has mode have PCS have these capabilities. And then you have your reactive power voltage, and it's any deviation of the voltage from 0.95 to 105, or changing dramatically in your power factor as well. In the UK, these are mandatory services through the obligatory reactive power services, or you have the enhanced reactive power services, which is being displayed at the moment, and is any drop of 2 to 7% of your reactive power. They are very fast dynamic response and very lucrative services at the moment as well, because being regional and depending where you have constrained the area, constrained areas, you tend to see the higher success rate for being called for these reactive power services. In Greece, it's mandatory and dynamic voltage at any deviation plus minus of 35% of your reactive power capabilities of your system. So I have been discussing a bit of the solution. We clearly see that renewable, having large penetration is actually of renewable energy sources is actually a benefit. The only piece missing in the puzzle is having the batteries to balance, or energy storage in general to balance. This is what the solution is going to cover, the problem of having the imbalance on the energy and the grid, which is going to translate into having better or enhanced energy security in Greece, plus enable Greece to meet the net CO2 zero target by 2050, which is being accelerated by ideally to 2030. The energy security is now the key critical point. It started with the net CO2 targets, but obviously through the recent geopolitical tensions, everyone has realized that, like, oh, we need to keep an eye on our interconnectors and dependency on electricity from neighboring countries. And that's why you guys are in a perfect situation, because having that large renewable energy penetration, by adding now more batteries, you're going to enhance your energy security. Now I'm going to pass you to Sanju, that is going to be talking about the alternative technologies within energy storage. Thank you.
Hi everyone, I'm Sanjay. I'm also a project consultant here at Blanbos, and for the latter half of this webinar, we're going to be covering three things. First, the alternatives to lithium-ion BESS. Second, how a project gets actually built and financed. And third, how batteries generate revenue, with an example from the Greek spot market prices last Tuesday. We'll start by zooming out on this slide. Lithium-ion gets all the headlines, but it's just one tool in the flexibility toolkit. To make smart decisions, we need to know what each technology is actually good for. The single most concept on this slide is duration matching. The question is never what's the best storage technology, it's what duration does my problem need. Lithium-ion BESS dominates the 1 to 4 hour range. It has fast response, high efficiency, established supply chain. Flow batteries sits in the 4 to 12 hour zone, longer daily cycling. They're all still scaling up commercially. Pumped hydro covers 6 hours to up to a full day. It's the king of pulse shifting, but you need the right topography. Liquid air and compressed air push into multi-day territory, and hydrogen and synthetic fuels are really only the credible option for seasonal storage. The rule of thumb to remember: below 4 hours, lithium wins in speed, efficiency, and maturity. Beyond 8 to 24 hours, around efficiency stops mattering so much, and what matters is the cost of adding more energy and site constraints. So when someone says we need long duration storage, energy storage, our first question really should be, what duration does my problem need? Next slide. This table is the engineer and investor's view of the same landscape. 3 columns matter most here: round trip efficiency, main constraint, and bankability. Starting with BESS, lithium-ion, 85 to 95% efficiency. It's very highly bankable. Pumped hydro, slightly lower efficiency, but still highly bankable because it's been done at scale for decades. Flow batteries, medium bankability, promising for longer cycling, but the supply chain is still small. Liquid air and compressed air, these are emerging, lower efficiency, lower bankability, but they unlock durations that batteries can't yet economically match. And hydrogen, 25 to 45% round trip, inefficient, but it's truly just for seasonal storage and industrial decarbonization. The strategic point is that we don't need to choose between BESS and long duration energy storage or other energy storage technologies. We need all of them. BESS handles the daily volatility, while pumped hydro and long duration storage technologies can handle the multi-hour and system adequacy gaps. So the alternatives are not better batteries, they're just different flexibility assets with different financing paths, different constraints, and different revenue stacks. Next slide, please. So we know what storage technologies exist and what each is good for. Now moving on to how a BESS project actually gets developed, financed, built, and where the real value is created. On this slide, we can see firstly why we need the battery storage and why it really matters now in Greece. Greece saw 6 to 7% renewable energy curtailment in 2025. That's more than double 2024. Solar is being switched off at midday because there's nowhere for the energy to go. And for 2026, there will be a possible 3.3 to 3.7 terawatt hours of curtailment. That's a research estimate, but the trajectory that we've seen in the recent weeks is very clear. And 4.7 gigawatt is the next growth phase. The focus is shifting towards unsubsidized and merchant projects. If you look at the chart, the commercial gap on the left, that's the systemic problem, where you can see midday solar surplus and evening scarcity. The morning and evening peaks are where flexibility gets paid. Midday is where energy gets wasted. A battery is fundamentally a machine that moves energy from wasted hours to valuable hours. And in terms of investment logic, you buy cheap curtailed power and sell when the system needs flexibility. And the grid constraint, the grid connection, and your route to market matter as much as the battery price. A cheap asset with no route to market is not bankable. Next slide, please. So we know the batteries prices are falling fast. That's the headline news, which is good, but here's the trap. This is the most important point on this slide. A turnkey battery price is never the same as an investable project cost. So when you see a $107 kilowatt hour figure, always ask, is that AC or DC? Is it a 2 hour or a 4 hour System, what's in the EPC scope, civils, grid works, fire system, what's the warranty and augmentation policy. Europe and Greece specifically adds premium for grid works, land and EPC margins. And the interconnection risk can dominate your IRR even when the battery itself is cheap. And the investor lens in this, the cheapest projects per megawatt hour is, again, almost never the one with the lowest battery price. It's the one with the right connection, right warranty, right availability guarantee, and a credible route to market. Moving on to the next slide. DevEx, CapEx, and OpEx, this is where the projected value is created. The three areas of cost, and they create value at different stages of the project. DevEx, the development cost, this includes land, grid application studies, permitting, legal work. This is small in absolute terms, but it's where you create real option value. A good key position and clean permits can make a project worth millions before a single battery is bought. CapEx, the build cost, this includes batteries, power conversion, transformers, civils, fire safety, grid works, EPC margin. This is where most of the cash leaves the project before any revenue starts. So cost certainty is the bankability gate. Lenders want fixed lump sum EPC wrapped contracts. And the OpEx, operating costs, the energy management system, the optimizer, the insurance, augmentation. This is where you defend revenues over 15 to 20 years. Availability, degradation, discipline, and cycling strategy decide whether your IRR will hold. The line at the bottom is the mental model that I want the students to live with. BESS is not just an electrical asset. It's a construction project plus a trading strategy plus a degradation model, all running simultaneously. Next slide, please. This slide indicates the indicated CapEx split for utility scale 4-hour BESS. So it starts with battery and containers, about 60%. This is the big one, and is the line item that has been falling. Power conversion plus transformers, about 10%. Civil and electrical BOP plus EPC margin, about 17%. Grid connection and substation, about 8%. DevEx, owner costs, and contingency, about 5%. These are indicative, so obviously every project differs. But three things to always note at this stage is what's the commercial translation. Always check inclusions and exclusions, grid works, land lease, fire system, spare parts, liquidated damages, taxes, bond costs. These are all factors that can move the numbers by 10 to 20%. And procurement watch-outs. What does the warranty interact with? Does the warranty interact with your cycling strategy? What's the augmentation policy? Is the PCS oversized? What's the AC/DC ratio? And the reality in Greece and every other country where you build a BESS. What's the key position and connection terms? Next slide, please. And moving on to the project life cycle, it's usually for every BESS project, there's 8 defined stages, which take roughly 36 to 48 months from site identification to commercial operation. Let me just walk through them quickly. We begin with finding a site. The wrong site kills the project. Land option and grid proximity matter. Second, grid application, TSO or DSO connection offer. Key position is really everything. Permitting, environmental impact, planning, fire studies, appeals can delay you by months. Moving on to FEED and tender stage. This is where the engineering, design, and EPC connection is completed. And moving on to final investment decision, FID, debt, equity, hedging, route to market, all locked here. And moving on, following that, we move on to construction, where most of the civil, container delivery, cabling is done. Here we have to specifically watch out for any liquidated damages. Then we move on to commissioning, where we complete grid code tasting, performance test, and a failed PT is a real risk. And finally, moving into operations, this is where you optimize and trade the BESS, and the strategy matters over the lifetime. But 4 big phases: development, brief, final investment decision, build, and operation. Next slide, please. So we have a good project and we need money to build the project. Generally, these are the key factors that any lenders or any banks or investor would look for a project. It's 4 certainties, and usually they want all 4. First of all, revenue certainty. What's the merchant forecast? Who's the optimizer? And what's the capture price risk? Moving into technical certainty. This includes warranty terms, degradation curve, fire safety design, and grid code compliance. Then delivery certainty. Is the EPC strong? What are the liquidated damages? Is the supply chain credible? What's the grid energization debt? And moving into operating certainty. Who's the operation and maintenance provider? availability guarantees, augmentation reserve, and data access. If any single of these areas is weak, the project becomes harder to finance and sometimes even impossible. The line at the bottom is a lesson. A low capex battery with a weak grid access or unclear market representation is not bankable. Technically excellent battery is not bankable unless the revenue and performance risks can be explained and allocated to a counterparty who can carry them. Moving on to next slide. So we'll move on to BESS markets. We've covered the technologies, how projects are built and financed, and let's move to understand how a battery actually generates revenue. Batteries revenue comes through a stack, not a single market, generally 5 layers in every country, including Greece, and they can evolve over time. First of all, we have day ahead and intraday arbitrage, where we buy at low prices, sell at high. This is the bread and butter of merchant BESS. Moving on to balancing market and BM flexibility. This is where you get paid to help the system and manage real-time imbalances. And moving on to ancillary services, this is the frequency response, like Andrews mentioned earlier. High margin today, but slowly compressing as more BESS enters market in every country. Moving on to capacity and adequacy payments, this is where you get fixed payments for just being and having your asset available. Hybrid PPAs and res firming, this is where you create co-located solar and wind assets, providing shape and forming to the grid. And the future layers would include grid forming services, any congestion management, and likely coming in within the next 3 to 5 years. The strategic insight in this is don't build a business case, especially BESS, on just one market. Ancillary services pay well now, but in the future, they will saturate quickly. And value will shift towards wholesale spreads, congestion management, and system services. And the design implication on the right, the stack is constrained, state of charge, availability windows, grid rules, and degradation all interact. You can't be in all 5 markets at once with the same megawatt hour. Moving on to the next slide. The chart here shows the Greek spot prices from last Tuesday, April 21st. Here, as you can see, the midday prices collapsed to 0. That's the solar curtailment problem we talked about earlier. Then there's a steep ramp up from 1600 to 1900 hours as solar drops out and demand begins to pick up. Then the peak hits at 2100 hours at 148 euros per megawatt hour. Referring to the best revenue stack in the last slide, only one stack was fired that day, the intraday arbitrage, where we captured 236 euros per megawatt hour net of degradation in a single cycle. The other 4 layers, balancing mechanism, ancillaries, capacity, and hybrid PPA shaping were all latent. They were available, but we didn't use them. And if we look at the equation on the right, this is what the whole merchant BESS business thesis is based on. One line: revenue equals sell price minus buy price times usable energy times run efficiency minus degradation. Plugging in the data from April 21st, traded intraday, where we sold at 148 euros, bought at 0 during the midday. We provided 2 megawatt hours of usable energy, and the system had a round trip, and we deduct that by 15 euros per cycle for degradation. That's 148 times 2 times 0.85. That equals 251 euros gross minus 15. So total of 236 euros net per megawatt in a single day. And that's just one layer of the stack. Balancing ancillaries, capacity, and hybrid, they're all the upside that remain in the revenue stack. And if we annualize the 236 net per megawatt over 250 to 350 cycles, we got real bankable electrical asset that not just solves a system and net zero problem, but generates strong revenue. Now I'll pass it on to Andres.
Wow, that was good. Thank you. So yeah, wrapping up. Apologies that we have to rattle through a bit at the end, but yeah, just conscious of your time, guys. So yeah, as we've been saying through this hour or so of presentation, we definitely need BESS, not only UK, Europe, but in Greece, as we have shown. to meet not only the net CO2 targets, but more importantly, at least for me, about energy security, but also to make the grid more efficient and ultimately you guys paying less for your every kilowatt hour of use. BESS, as Sanji mentioned, is a very profitable business and is also being proved in the UK and more mature markets. The case of the April 21st example shows a single layer of revenue just paying to 236 euros per megawatt, which is quite substantial when you compare it to other markets. Lithium ion, apologies for those that may disagree because this is a very controversial point, but I'm very adamant to this. Lithium ion will be king at least until 2030. But obviously other chemistry will make their way. As Sanju and Harry mentioned, the idea is not that one has to replace the other. It's not that all of them have to work together for different needs. And obviously the wholesale electricity market will be the primary revenue source, while frequency services will be minimal. So now we open the floor for you guys. If you have any questions, please feel free. Again, Yorgos, I'm conscious of the time, but let me know. I'm more than happy to follow up with questions and whatnot.
That's great, guys. Thank you, Andres, Harry, and your colleague, and Sanjay, for a very interesting presentation. I have a few questions, but I want to see first if there is a questions from the floor. Guys and gals. Anything, any questions?
Don't be shy.
I will, yes. Yes, exactly, don't be shy.
I have a question. What happens after the end cycle of the project, after the 15 years?
Did you hear the questions, guys?
Is it what happens after the 15 years, right?
Yes.
Yeah, I'll take that one, guys. Yeah, very, very good question. Technically speaking, depends how your contract is set up, but in very normalized style, what happens is that the battery supplier will not give you any reliance on the equipment. And because for them, the declaration of the state of health that Harry mentioned have reached the limit, they see the project as a unsafe project, especially lithium ion or LFP that can be very prone to fire or any issues. So basically what happens is that the project gets decommissioned and it has to move through the recycling stage. And the recycling stage on its own is another very important and interesting topic because at the moment, even though that we have the EU regulations and the battery regulation in terms of recycling, which dictates that batteries have to be recycled within the European Union, still we don't know very precisely the mechanism involved and more importantly the cost. But in theory, the process is that you have to decommission the whole plant and then or either give a second use to the battery or you have to recycle.
So for your current projects, you don't have any mandatory mandate anyway to recycle.
No, you have a mandate. It has to be recycled. It cannot be like shipped to any other country outside, at least in the UK, outside the UK, or outside Europe for recycling. It has to be recycled within the region, and the mandate sits with the importer of the equipment. It doesn't state it has to be the 15 years. It's just whenever it needs to be recycled.
Okay. Any other questions? Anything? Everything was clear, Andres. The guy.
I should be a lecturer.
Crystal clear. Yeah. So Apostolis here is asking, what is the next chemistry, battery chemistry, after what's the trend in the next technology for batteries after lithium?
I leave that to Harry.
Yeah, so the one that we're seeing the most is sodium ion. So last year they had 9 gigawatt hours factory shipments, and that's just ramping up more and more. Especially the Chinese suppliers, Catel and BYD, they've like ramped up their manufacturing significantly, and it looks like that's the next one that's going to be taking us 2030 onwards at the moment. So that's
Yeah.
sodium ion.
Yeah, and to add to that point, like a few years ago, it was more like, oh, it's just still at R&D stage and it's gonna be difficult to be heavily commercialized. That's not definitely the case anymore. The thing is that LFP is putting a very difficult case to other chemistries. We also have like redox flow batteries, or what we call flow batteries, that are more electromechanical systems that in terms of efficiency are very ideal, but the big challenge is that price wise they haven't been able to compete against the price of LFP. And the LFP, what is actually driving very well the prices, is not only actually the energy storage or grid applications is very minimal, is the EV industry that is pulling these prices down. But what is happening now is that sodium is also entering this market, which is going to bring the prices down. And that's why we see that it's going to be the next one very soon. I'd say 2030, but some other people are more optimistic that it could be within the decade that you're going to start seeing them competing against LFP.
Continuing to this question, I was wondering why the bankability of alternative battery systems like hydro and liquid or compressed air is so low.
Yeah, it's actually a good question. And I think it depends of the trust and the technology. And this is not all saying that, like, for example, air compressed air, I think is highly efficient. But the thing is the trust that lenders have on these technologies. And sometimes they don't follow what, let's say, without diminishing the let's say the capabilities, but it's the lack of understanding of the technology, not only from the technical aspect, but also for the confidence in the industry for banks or lenders to invest, or any investors. And the same happened with battery. When I started back in 2015, you will talk about batteries and people will just say you're talking about futuristic stuff that will never happen. It's because there was no like a proven area to say actually this can be bankable, because you have enough solid warranties, enough protection for your investment, and therefore there is a solid market for this. So there needs to be more development on that side, more incentivization to the industry, that there is a clear path within the market, and also for the lenders to feel, or investors to feel, more secure through their investment. I don't know, Sanju or Harry, if you have another point that you would like to add on this.
I think it just comes down to the maturity of it. I know there are examples of projects, especially hydro pumped, it's definitely mature and proven that it is bankable. But there's also a lot of infrastructure with those that you maybe don't see, and like the geography needs to be right for some of those technologies, and might have a longer lifetime as well, which has more impacts to consider. So, yeah, I think at the moment,
Sorry, go on.
Just batteries seem to be having their moment at the moment, particularly in the UK, and I think that's just snowballing.
Yeah, and I think another final point to add on this, George, was that it is quite interesting, and it goes a bit related to what Sanju was saying, is also the market volatility. The market opportunity in the free energy market is moving really fast, and new services are coming up, and which obviously those that are going to be able to capture them profit and benefit of the profit are those more mature technologies. So perhaps these technologies are going to be better suited, as Harry mentioned, depending on the geography, not only on that, but also on the economy side, what security you can have, where if you may have more an access to a power purchase agreement, which is fixed through the years, rather than having to enter in free energy markets, because otherwise having the time, what it takes to build one of these projects is very difficult to predict what your revenues are going to be, unless you were to have a secure PPA.
Yeah,
Changes the dynamic a bit.
We see that also in the feeding in the support in Greece, in the supported systems for batteries. It's only batteries. From my experience, it's only batteries that are supported. And of course, yes, the maturity of the technologies.
Yeah.
The main reason and the main stopper for other technologies, which is on the other hand the only option for research and development and thus universities to work on these technologies, on alternative technologies.
Yeah, because also, even though that we preach and evangelize a lot about batteries, and I agree with you, it should also not be the only one. We should also be investing in other type of technologies, because at the end of the day, what it matters here is what we consumers are paying and what is the reliance of our grids. So the more access to technologies we can have, and less dependency, because one drawback of batteries that is heavily dependent in one country as to where you can source your battery cells. So that straight away puts you in some way into a constraint if anything were to happen geopolitically speaking. So having less dependency would be directly linked to have a greater access to other technologies to offer the same support.
Do you have a more complete picture for country-wise? What is the capacity of storage, especially I guess it's especially high in countries with high renewable penetration. Is that right?
Yes, obviously you see a link, as you said, countries that have a larger access to renewable energy penetration, there is a good opening for capacity for batteries. But interestingly enough, those countries, the energy market is still not open or mature enough for batteries to participate, which is for the likes of Spain, where Italy is getting a bit better, Germany is kind of ramping up, but it's still less mature. I think they are a bit skeptical as to what is happening, but obviously now you have markets like the US, UK, that have been benefit not only from the perspective of the energy market, but also from the grid side, that are able to reduce their cost by passing that to the market and having to procure or balancing their grid that otherwise would have been investment from them directly by just buying those services. So, sorry, probably deviate a bit on the question. The straight answer, we don't have those numbers per se, but the correlation goes that way. Higher renewable energy sources of penetration generation, the more likely you're going to have access to or opportunities for batteries, but it will depend on the market.
Any other questions, guys? Yeah.
Αν τώρα με αυτή την κρίση που έγινε με τον πόλεμο και την αυτά, αν οι ευρωπαϊκές χώρες κάνει κάποιες μεγάλες αγορές.
There is another question. How did the the recent crisis and the yes, in oil, in oil price and everything, affected any procurement for BESS?
It's a very good question. It does somehow, somewhere in the supply chain, but still, and I'm not talking for the industry, just for the projects of what we have seen, it's like we haven't seen still the actual true impact. And definitely, depending on where the location of the project is, there has been a bit of some nervousness of what is going on, like particularly these very large projects in the Middle East. A lot of these have been put on hold at the moment, as far as I'm aware. We are not directly involved in any of these projects, but at least in the UK, Germany, Italy, we haven't seen anything in this regard. And this can also be because the main supplier, I'm talking predominantly Chinese suppliers, they tend to work in a surplus of production, that we are only eating that surplus and we're not seeing that impact. But definitely somewhere down the line, we're going to see it. And it does scare investors. And that probably the appetite to invest is being reduced gradually, just to see what the world is going to be doing with this situation.
I guess this has to do also with, I mean, timescales of these large projects. I was going to ask, what are the timescales for your projects? I mean, from pre-development to pre-PID, as you call it, and building. What timescales are we talking about here?
You want to take this one, Sanju?
Huh?
I'm asking Sanju if he wants to take it or you want me to take it.
I can provide some color, sure. I think generally from the projects that we've been involved in, usually I guess the average is around 36 to 48 months, but what countries where there's like less regulatory hurdles to jump through, usually that timescale can be like brought down quickly. And I'll pass on to Andres if you wanted to add anything to that.
Yeah, so you tend to see those timelines, especially for very large projects or very remote areas. And like in the UK, the thing is, in the UK is not, let's say, the best example, because everything now has been kind of well standardized. Well, I say well standardized, but we have the experience nowadays. So you can actually bring that down to 2 years. Like, for example, we are working in a 500 megawatt project that, without taking into the delays from the grid operator or the TSO in this case, the project would have been 2 years from FID. So there's your money, guys, contract signed, built. It would have been 2 years, 500 megawatt. So you see that as a really fast for a large project. And not even, well, probably in solar, you may be able to do 500 megawatt in 2 years.